Quasi-Monte Carlo methods are an extension of traditional Monte Carlo techniques that improve accuracy by using low discrepancy sequences instead of purely random sampling. These methods provide more evenly distributed points, leading to faster convergence and more reliable estimates. What are quasi-Monte Carlo methods? Traditional Monte Carlo methods rely on purely random samples, which can sometimes cluster unevenly. This can lead to inefficiencies and higher variance in the results. Quasi-Monte Carlo methods address this by using specially designed sequences that fill the space more uniformly, reducing errors. Difference between Monte Carlo and Quasi-Monte Carlo. Monte Carlo methods use random sampling, which can be effective but may require a large number of samples to achieve accuracy. Quasi-Monte Carlo methods use deterministic low discrepancy sequences such as Sobol or Halton sequences, which distribute points more evenly and reduce variance. Advantages of Quasi-Monte Carlo methods. They provide faster convergence than standard Monte Carlo methods, meaning fewer samples are needed to achieve the same level of accuracy. They produce more stable and consistent results because the sampling process is structured. They work well in high-dimensional problems, making them ideal for applications in finance, physics, and engineering. Examples of low discrepancy sequences. One common sequence is the Sobol sequence, which is widely used in scientific computing and numerical integration. It ensures that points are spread out evenly across a given space. Another example is the Halton sequence, which is particularly useful in lower dimensional problems. Applications of quasi-Monte Carlo methods. In finance, they are used for pricing complex financial derivatives and risk assessment. In computer graphics, they improve rendering techniques by reducing noise in light simulations. In engineering, they assist in optimizing design simulations and solving high-dimensional integration problems. Limitations of quasi-Monte Carlo methods. Despite their advantages, these methods require careful selection of sequences to avoid issues in high dimensions. They may not work as effectively for problems that rely heavily on randomness, such as certain stochastic simulations. Conclusion. Quasi-Monte Carlo methods improve the efficiency of Monte Carlo simulations by using structured sampling techniques. They offer faster convergence and more reliable results in many applications, making them a valuable tool in scientific computing, finance, and engineering.